So now our whole structure free body diagram again looks like the following, right? All the 3 red arrows are still present over at the wall. We've solved for the roller force, which is equal to 8.5 kilonewtons. And so now the most efficient way to do this is really just to do statics. So again, we can now solve for those 3 red arrows. We have not used any equations of equilibrium yet on this whole structure free body diagram. So we can kind of knock this out quickly. Some of the forces in the x direction obviously gives us that F1 equals 0. I can sum forces in the y direction. That equals 0. And again, to do that, I'm going to end up representing the distributed load as a statically equivalent point load. Its value would be 2 times 6, which is equal to, again, 12 kilonewtons. Right? Its placement would be at 3 meters. So if I sum forces in the y direction, I end up with a solution for F2. It's going to be 3.5 kilonewtons, right? Or 3.5 kilonewtons up. And so to solve for the moment, I can go ahead and spin a moment at the left end. And again, I'm going to have in that equation M1, I'm going to have the distributed load and the 8.5 kilonewton load. So you see how my distributed load has shown up as a statically equivalent point load with its lever arm. And now again, we've got sign convention to adhere to, so that's why we have a negative sign in front of M1. And we're able to solve for M1. It's positive. And that relates back to the free body diagram that I've drawn. So that means that it is going to be going in the counterclockwise direction. So now we've got a solved free body diagram right there. And so what we'd want to do though is check that we actually have a free body diagram that's in equilibrium. So again, we have an infinite number of equations of equilibrium. We've used 3. And so we just need to choose another one. And so what I'm going to do is sum moments over here at the right end. And let's just check that we end up getting 0. So if you want to write this equation, maybe pause and go ahead and do it. Again, here's your answer for summing moments at the right end. Right? You'd have a contribution from the applied moment over at the left end. There's the vertical force at the left end times 6 meters. And you see the rest of the contributions. Again, you see the representation of the distributed load as a 12 kilonewton statically equivalent point load. And if we do the math the rest of the way, we would find that 0 equals 0 indeed. So we have a solved free body diagram. Draw the shear and the moment diagram for this beam. So I have a shear diagram. We've got units of kilonewton. Right, there's our sign convention, left side of the V. So I'm going to work my way left to right across this beam. As I get onto the beam, I encounter immediately a load that kicks me up to 3.5 kilonewtons. And then as I keep moving across the beam, I'm in the middle of a distributed load. So over those 4 meters, I end up with a net movement of 8 kilonewtons down. So I'm just going to drop down a guideline. And so over here, I would end up at minus 4.5. So again, the change from the left end of the beam to 4 meters is going to be the area underneath the distributed load, which is going to be 2 kilonewtons per meter times 4 meters. So I can go ahead and draw my connecting point. Then at the 4 meter mark, I run into a point load of 8.5. That's going to kick me up to 8.5. And I end up at positive 4. Over the last 2 meters, I have a distributed load, net effect being 2 kilonewton per meter times 2 of 4. So I end up with a change of 4, which takes me back to 0. So I'm going to go ahead and draw that vertical discontinuity in, and then I can just kind of hatch in my shear diagram. So to set ourselves up to go from the shear diagram to the moment diagram, we're going to end up calculating some areas, because we know that the change in the moment between any 2 points is going to be equal to the area underneath the shear diagram. So we've got some need to calculate some areas here. And if we look at A1 and A2, we have the need to come up with that distance x so that we can find the area of that triangle. So to do that, we're going to use similar triangles. So I've got 3.5 over a distance x is going to be similar to a total change of 8 over a distance 4. And you kind of see that bigger triangle sitting right there. And so our similar triangles would mean that 3.5 over x would have to be equal to 8 over 4. And so that would mean that 3.5 is going to be equal to 2x. So that means that x is going to be equal to 1.75. So now back up here, I can go solve for my areas. Area 1 is going to be 1/2 the base, which is 1.75 times 3.5. So that's going to give me an answer of plus 3.063. A2 is going to be 1/2 the base, which would have a distance of 4 minus 1.75 times a height of minus 4.5. That gives me a total area of minus 5.063. And we see A3 is equal to 1/2 base, which is 2, height of 4, giving us an answer of positive 4. So we're going to end up using these areas as we work our way across the moment diagram. So let's go back up here and look at our solved free body diagram. We just take a couple of scratches off here. And so if we look at our moment diagram again, or our solved free body diagram, right, we're going to work left to right across our beam. And as we get on the beam, we immediately encounter an applied moment. That applied moment would be causing our beam to bend down, which would be negative, right, or an unhappy face. So if we look at our moment diagram, right, our moment diagram first would have units of kilonewton meters. And immediately when we jump onto that thing, we get a value of -2. And so what we're going to do is use these areas up here, A1, A2, and A3. And so we're going to do these calculations right below down here. So the moment at 1.75, and the reason why we're going to use that is because we have got, a point of 0 shear, which is going to give us a maximum moment. And so this looks like the area A1. So the moment at 1.75 minus the moment at 0 has to be plus 3.06. And so I know that the moment at 0 is equal to -2. And so I go ahead and plug that in, and I then find that the moment at 1.75 is equal to positive 1.063. And I'm going to connect those two, not with a straight line, but with a curved line. And why is it going to be curved? Because the slope of the moment diagram is equal to the value of the shear diagram. So if we looked right at the beginning when we jump on, we have a very positive slope. As we get right to 1.75, we have a 0 slope. As we keep moving forward, our slope is going to get more and more negative. And so I'm going to solve for the moment at 4 by using the area in under the shear diagram between 1.75 and 4. And so we had found A2 is equal to minus 5.063. And so if I just plug in those values, I end up with the value for the moment at 4 equal to negative 4. And again, I'm going to connect those with a curved line going from 0 slope down to a very negative slope right at 4. And so let's kind of take a little bit of a look back at our shear diagram. Right? We have a vertical discontinuity. We have an instantaneous change in the slope of our moment diagram to where it goes from something that was very negative now to something that's very positive. And so I'm going to now calculate the moment at 6 relative to the moment at 4. That has to be equal to A3, which we found was positive 4. So we go ahead and plug in our values for the moment at 4, which was negative 4, and we find out that our moment diagram closes. So right at the end, we end up with 0. And the way I'm going to connect those is with a curved line, and that curved line is going to have a very positive slope. Let's go back and kind of look at our shear diagram. Very positive slope, all the way down to a 0 slope at the end. So I can kind of hatch in our moment diagram. So the very last thing we're going to do is draw the deflected shape for our beam. And so we're going to use that moment diagram that we just came up with a moment ago. And so I'm going to identify just a couple of points here. And so I'm highlighting points on our beam that have m equal to 0, which would mean that the curvature is equal to 0. So we have a change in curvature. So again, following our sign convention, we've got a beam with a negative curvature or an unhappy face. We have a positive curvature, and then it comes back over to a negative curvature. So again, our deflected shape is a qualitative representation of v of x. And so I need to stick to my boundary conditions. I know at the roller, I'm going to have 0 transverse deflection. I know at the wall, I'm going to have two things. I'm going to have 0 transverse deflection and 0 slope. So let's just kind of work our way across the beam. I'm going to end up with something that has a negative slope to it, transitioning then to a region with positive slope. Then it's going to transition again back to negative slope. So then I can kind of fill that in. And again, this is just qualitatively based. I'm not claiming that the deflection out there at the end of the beam is actually down. It could be up, but all we've done is just followed curvatures here and our boundary conditions. So this would be a sketch of the deflected shape for our beam.